Today we're going to break down how Bitcoin and Ethereum actually store transactions and why they use something called a Merkle tree to do it. At its core, a blockchain is just a chain of blocks. You can think of each block like a digital box. Inside that box, there are two main compartments. The first one, called the body, holds all the transactions. That's where you'll find Alice pays Bob, Bob pays Charlie, and so on. The second compartment is the header, which doesn't store transactions directly, but instead stores metadata, extra information that helps the network quickly verify the block. And one of the most important pieces inside this header is something called the Merkle root. So what exactly is a Merkle root? Imagine you had a stack of thousands of receipts from a store. You want to prove later that one specific receipt was really in that pile without showing all of them. The Merkle root works like a master fingerprint for all those receipts. It's created using a special data structure called a Merkle tree. Here's how it works step by step. First, every transaction is passed through a hash function. A hash is just a way of turning any data, like Alice sends Bob 2.5 Ether, into a short, fixed-length string of numbers and letters. If the input changes even slightly, the output hash looks completely different. These transaction hashes form the leaves at the bottom of the tree. Then we take pairs of those hashes, stick them together, and hash them again. That gives us a new set of nodes, one level higher. We repeat the process layer by layer, pair, combine, hash again. Eventually, at the very top, there's only one hash left. That's the Merkle root, a single fingerprint that uniquely represents every single transaction in that block. Now, here's why this is so clever. If even one transaction changes, say Alice was paying Bob 2.5 Ether, but someone tries to edit it to 3 Ether, its hash completely changes. That difference ripples upward, changing its parent hash, then the next parent, and eventually the Merkle root. So by checking just that one number, the root, the network can instantly detect if anything inside the block has been tampered with. But, you might ask, couldn't we just take all the transactions, mash them together, and hash the whole list once? That would also give us a fingerprint that changes if anything changes. True. But here's the catch. A single giant hash doesn't let you prove inclusion efficiently. Imagine a block with 5,000 transactions. If you want to prove that transaction number 2,763 is inside, you'd have to reveal every single transaction in the block and recompute the giant hash. That's huge and impractical. The Merkle tree solves this with something called a Merkle proof. To prove one transaction is included, you only need its hash plus the small set of sibling hashes along its path to the root. That might be 10 or 15 hashes instead of thousands. It's like showing just a few key puzzle pieces to prove the entire picture is correct. This is especially powerful for what are called light clients, wallets or apps that don't store the full blockchain, but still want to verify transactions securely. With Merkle proofs, they can do this with very little data, and this becomes especially useful for huge Merkle trees containing thousands of transactions. And it's not just blockchains. Merkle trees are everywhere. Git, the version control system for code, also uses a Merkle-like structure. Each file change is hashed, and those hashes are combined, making it easy to track exactly when and where changes happened. That's why Git can so quickly spot differences between two versions of a project. So to sum it all up, the Merkle tree gives blockchains their unique superpower and security, efficiency, and scalability. It allows Bitcoin, Ethereum, and other networks to prove what's inside a block without exposing everything. And it keeps verification fast even as blocks grow to thousands of transactions. Without it, verifying transactions would be slow, heavy, and way more expensive.